So my name is Anton, and I would like to go through the third assignment, which is about simulating the flow past a cylinder. And the first part, we was given this block mesh dict file, which creates this mesh, and we had to learn how to control it. And we did this by editing this section of the block mesh dict file. And the way this works is that it creates all these different blocks based on vertices, which has been defined previously based on the coordinates. So basically, we had a block, we would have blocks here and so on. So all these different blocks. And the next numbers would indicate the number of cells in each direction. So that is the X, Y, and Z direction. And then that will also indicate a gradient in each direction. Now, when creating the different meshes that we use later for the mesh independency analysis, it was very important to ensure that the number of subdivisions of neighboring blocks would match. So that was the tricky part. And here we see an example of a refined mesh where we put an emphasis on refining in the area of where the vortex shedding and around the cylinder. Next up, we had to set up the simulation, and first and foremost, we had to ensure that we had the specified Reynolds number of 100. And since the cylinder diameter was fixed, we could only change the viscosity and the flow velocity. The way the flow velocity was controlled is through this file U, which controls the boundary conditions and inlet conditions for the velocity. And the code would look something like this, where it indicate at the inlet, the velocity to be 1 meter a second in the X direction. All these different names is also something that was specified in the block mesh dict file. And additionally, we can see all the different boundary conditions. So in and around at the boundary of the cylinder, we would like to have no slip, for example. The kinematic viscosity is adjusted in a separate file where we indicate the value and units. And also we had to specify the initial and boundary conditions of the pressure, which is done in a similar way to the initial velocity, but obviously with different boundary conditions. Now we had to control some of our simulation parameters, which is done in the control dict file. And we want to use an openFoam solver since it's an unsteady problem. And the openFoam solver can be used for incompressible flows, which this is. We also indicated a start and end time and step size, which is something that we will control later in the step size independency analysis. Additionally, this is also where we extract our max and lift, drag and lift coefficients, and also our residuals. That is this part from line 32 and below. Now, we'd like to specify our different discretization schemes. So for example, this first part for the DDT schemes, which are the temporal terms with like a backbone Euler. And for the gradient term, which is the pressure gradient, we want this second order Gauss linear method, and so on. All these different terms, so Laplacian is the diffusive terms. Now, moving on, for the FV solution file, we specify the solver settings. So we specify a certain solver, and then when we use a piezo solver, which is the group that openFoam is in, we have these inner iteration loops where we need to specify a tolerance until it moves on to the next inner iteration. So that is what this value is for the pressure. And further down, we have the solver and the tolerance for the velocity as well. Now for the piezo solver, as mentioned, we have these inner loops and this number indicates the amount of these. So we chose 2, which is also something that we investigated, and I'll show some plots of a bit further down. Now for task 1.3, we had to extract the lift and drag coefficients. And for example, for this lift, it looks something like this. And we can see that heavy oscillations start to occur. And around this point, for the 60 seconds, something like that, we see this vortex shedding phenomenon. Now we were interested in using this maximum lift coefficient for our independency analysis. This is the drag coefficient plot. You can see that it also starts to oscillate here, and we get a maximum drag coefficient of about 1.42. As mentioned previously, we had this residual plot as well. Basically, we wanted to do this to ensure that we had a solution that we can basically trust that it was converged. And the way we do this is by considering if the pressure is below 10 to the power of -3, which it is, and that the velocity should be below 10 to the power of -5, which it also is. So the simulation should be successful. Now for the independency analysis. And firstly, we had this mesh dependency analysis, and the way we performed the mesh independency analysis was by trying different mesh sizes. And once we found that a doubling of the cell count did not produce result that was more than 5% different than the original cell count, then we would deem that mesh to be independent. So comparing this, or the 5% boundaries with this point, we deem this point to be, or this mesh to be sufficiently fine, which corresponds to a cell count of 12,100 cells. We also checked the drag coefficients just to be sure. And then we did the time step dependency analysis in a very similar way. We found that a doubling and even a quadrupling of the number of time steps from 10,000 time steps did not produce sufficiently different results. So we went with 10,000 time steps, which corresponds to a delta t of 0.02 seconds. And we also wanted to investigate what the number of inner loops in the piece of foam solver, what the effect of that would be. And we found that the 2 inner loops was sufficient. Moving on, we had to investigate the Struhal number, which needs this oscillation frequency, which we can get from our simulation using this fast Fourier transform. And what we found is that we had an oscillation frequency that was 0.188 hertz. And thus a Struhal number that was 0.188. Then we could compare that to an empirical relation. And we found that these two numbers were only 2.7% different. And then moving on, we had to also validate our lift and drag coefficient against multiple different literatures. And we found that our result in general is a bit above, which there can be multiple reasons to. We generally found maybe the mesh and step size was partly responsible, but in general, even the converged value seems to lie above the literature. But we also find that the Struhal number used in some of these is a bit different than the ones we found. Yeah. And lastly, we just have some figures where we show for our validated results, which was 12,100 cells, 2 correctors, and a delta t of 0.02 seconds. We get this velocity field, and we also visualized the streamlines. And yeah, that's it.